Um, so with a single variable function, so uh, if we have y equals some function of x, or and x equals some function of t, the chain rule tells us that dy dt equals dy dx dx dt. So this is something that you've been using for a long time. For multivariable functions, just like we have several cases for our second partial derivative, we have several cases for the chain rule, depending on how our function varies, how our function depends on our other variables. So we're going to talk about several different cases for chain rules. So our case one. Our case one is we have z equals some function of x and y. And x equals some function of t. And y is some other function of t. So z is indirectly a function of t. So we need to, if we're taking our derivative of z with respect to x and y, we need to take into account how x and y vary with t. So our assumptions for this case, so we're assuming our assumptions are that z, g, and h are differentiable, and that, and again, z being differentiable implies that f, the partial with respect to x, and the partial with respect to y are continuous. This assumption guarantees us that this is the case, and that for case 1, dz dt equals dz dx dx dt plus dz dy dy dt. So this is our first case where we have a two-variable function, and each variable is in turn a function of a single other variable. So x and y are some functions of t, some other single variable. So this is our chain rule for that case. Now we can have more complicated dependencies in our variables. So let's look at that a case for that one. Any questions on this part? All right, so case 2. Case 2, we have a little more complicated dependency. We have z equals f of x, y. And x is some function of two variables. And y is a function of two variables as well. So z is indirectly a function of s and t. Z varies as s and t varies. And we want to find dz ds and dz dt. So we're going to apply case 1, our first case, to each of these partial derivatives, and see what we come up with. So our assumptions again. Our assumptions are that z, g, and h are differentiable. And we're going to apply case 1 that we just talked about to each of these partials. So dz ds equals dz dx, dx ds plus dz dy dy ds, and dz dt equals dz dx dx dt plus dz dy dy dt. And when we do these chain rules, we want to then, when we evaluate these derivatives, we want our final answer to be in terms of our original variables. So if we continue, if we have a 3-variable function, or if x and y are functions of more than one variable, we have these chain rules get more and more complicated. We have more and more terms. The way to keep track of our partial derivatives, we can use what we call a tree diagram. So we'll write tree diagrams for our different cases, and then talk about a more general case. Questions on this so far? All right, so tree diagrams help us keep track of our partial derivatives. So for our tree diagrams, z is the dependent variable. X and y are the intermediate variables. And S and T are the independent variables. And I think I spelled this wrong. So we start for our tree diagram, we start with our dependent variable. Need to start closer to the middle. Here are intermediate variables, x and y. So to get, when we're taking our partial derivative to get from z to x, we're going to do dz dx. And for this side, we do dz dy. And then our independent variables are s and t. So this is dx ds, and this is dx dt, and dy ds, and dy dt. So we have our dependent, intermediate, and independent. So we just follow, to find the derivative that we're interested in, we follow along the branches that we want and add the results. So if we want dz ds, we need dz dx, dx ds. And we just follow along the branches. And that's what we just wrote down. Questions on our tree diagram. So if we have a function that varies with several variables, and each of those variables in turn varies with other variables, we could go as many steps as we wanted. But the tree diagram would help us keep track of how we need to put together our diagram. Any questions on that part? So if we have more than two variables, it's the same idea. Our tree would just have more branches. But if we wanted, for example, if we want dz dt, we just follow along dz dx, dx dt, and dz dy, dy dt. And we add those two results, and that's going to give us dz dt. If we have a function of 3 variables, we're going to have 3 terms. If we have a function of 4 variables, we're going to have 4 terms. But the same pattern holds. No questions? So we can use the chain rule to simplify implicit differentiation. So remember when you've talked about implicit differentiation in the past, we had some function that wasn't written explicitly in terms of x. We didn't have f of x equals x squared plus 3x plus 5. We had f of x. We had some function like x squared plus 2xy plus 3y squared over xy, and we wanted to find dy dx for that particular function. So our function was not explicitly defined, so we had to use implicit differentiation to figure out our derivative. Partial derivatives can help us out with that. So let's say we have some function, f of xy, equal to 0. And we assume that y is an implicit function of x. So we're saying y equals some function of x. It has some kind of functional dependence. So we can write our original function, f of x equals 0. This is x and this is y. And we're going to apply case 1 of the chain rule. So we're going to apply case 1 to this function. So df dx, and remember our function equals 0, that's important here. Df dx, dx dx, plus df dy, dy dx equals 0. And I could have written, just since y is just a function of a single variable, I could have written our regular straight d's for these derivatives. But dx dx is just 1. So I can simplify this. So dy dx equals minus df dx over df dy. And we have to have df dy not equal to 0. So think about some complicated function, that if we had some function where y is implicitly a function of x. So say we had something like x cubed y plus 3x squared y to the 4th minus the natural log of xy. And we wanted to figure out dy dx. So to figure out dy dx the way we did it before, you would have to do implicit differentiation on this particular function and solve for y prime. That would be kind of ugly. But with this simplification, using partial derivatives, we have a much easier way to do this. So I'm just going to use that example. We don't need to worry about that. I'm not going to do that problem. And if we have a multivariable function, or sorry, a 3-variable function, or more, if f of x, y, z equals 0, and z is implicitly some function of x and y, we can go through a similar argument to find our partials of z with respect to x. So going through a similar argument, we would say dz dx is minus f sub x over f sub z, and dz dy equals minus the partial of f with respect to y over the partial of f with respect to z. So using partial derivatives can help us evaluate these implicit differentiation problems. Questions on this? All right, let's look at a few examples. So we have w equals y cubed minus 3x squared y, and x equals e to the s, and y equals e to the t. And let's say we're looking at the point s equals 0 and t equals 1. We want to find dw ds and dw dt. At this particular point. So dw ds, to find our first partial derivative, dw ds is going to be, by our chain rule, is going to be dw dx dx ds plus dw dy dy ds and dw dt is going to be dw dx dx dt plus dw dy dy dt. So we need to calculate a bunch of partial derivatives. So dw dx, dw dx is going to be what? Minus 6xy. dw dw dy 3y squared minus 3x squared. Dx ds is just going to be e to the s, and dx dt, we need dx dt for this one, going to be 0, and dy ds equals 0. dy dt is just e to the t. So now we can plug in and get all of our derivatives. So dw ds is dw dx, so it's minus 6xy times dx ds times e to the s plus dw dy times dx ds, and dx ds was, or I'm sorry, dy ds was 0. So we just have minus 6xy e to the s, and at s equals 0 and t equals 1, when x is 0 and t equals 1, x equals 1, y equals e. So dw ds is just minus 6e. And dw dt,
wait, e to the s is e to the 0, is not 1.
right?
Right, so
But y is e to the t, and t is 1. So that would be e.
right, oh, wait, here's y, oh.
Right.
I gotcha.
Okay? All right, and dw dt, if I plug in here, I get 3y squared minus 3x squared e to the t. And when I plug in my, at s equals 0 and t equals 1, this equals 3e e squared minus 1. Are we good on this? Okay. Let's look at an example using implicit differentiation.
Wait, so what did we just use?
What's that? Okay. All right. Let's look at an example of implicit differentiation. We have e to the xy, or I'm sorry, e to the xz plus xy equals 0. And this tells us z, we could, if we worked really hard, we could solve for z in terms of x and y for this function. So z is implicitly a function of x and y. We want to differentiate implicitly to find the first partials of z. So we want to find dz dx and dz dy. So without using partial derivatives, we have a method that we could use to find z in terms of x and y. We could take the derivative, or take the derivative of this with respect to x and use implicit differentiation and solve for z prime. We know how to do that. But with partial derivatives and the rule that we just used, we can simplify our work a lot. We know that dz dx is minus the partial of the function with respect to x over f, the partial of the function with respect to z, and dz dy is minus f sub y over f sub z. And what I'm saying, what we've written here, this is equivalent to saying that f of xy is equal to 0. Or sorry, f of xyz is equal to 0. So this satisfies our condition for using our first case on our partial derivatives here. So we can take the partial of this function, the partials of this function, to find our derivatives here. So f sub x, the partial derivative of this function with respect to x is what? Z e to the xz plus y. F sub y, partial with respect to y, is just x. The partial with respect to z is just going to be x e to the xz. So now I have all the pieces that I need for this. So dz dx is minus z e to the xz plus y over x e to the xz. Dz dy partial with respect to y, x over, sorry, minus x over x e to the xz, which is just 1 over e to the xz. Much easier than using the other method that we could possibly use to find the partial of z with respect to x. Any questions? All right, so we're getting towards, we're building our tools for taking derivatives of multivariable functions. We're getting towards the kind of the big idea that we want to get from this chapter. A couple of the big ideas. Next time on Friday. On Friday, we're going to talk about directional derivatives and gradients, and that's going to be an important concept for this chapter and for the last chapter that we do. And I know if you're in physics, if you're in Mr. Lowe's class, you've talked about the gradient, you've talked about the del operator, the upside down triangle, a little bit, and we're going to do a lot of work with that. And then we're going to talk about how we find maximum and minimum values of multivariable functions, because when we're talking about derivatives, that's one of our main goals for working with derivatives is maximizing and minimizing functions. So those are the two big things that we're going to do for the remainder of the chapter. Let's talk about direct. What's that?
Is our test on Thursday?
No, our test is not next Thursday, but the Thursday following, yeah. So the 1st and the 2nd is when our test is. We have a couple of days off from school coming up as well. Right. There's President's Day and then a teacher work day. So today's homework.